Okay, hello everyone. This is a lesson to go over, or a video to go over lesson 3 on implicit differentiation. So on my screen here, I have an implicit relation between x and y. So it's not something we're used to seeing normally when we have an equation. At a graph, we have the format sort of y equals and then some function of x. Here we have x squared plus y squared equals 25. So the y is written within the equation. So you can get some really cool shapes for your graph. So this is a circle, for example. You can make it into an ellipse by adding a constant there. You can make other cool functions. I don't even know what this is going to do. Oh, there we go. You can make other cool shapes in this way that don't look like it's sort of a typical graph. Some of them aren't even technically functions because they don't pass that vertical line test. So that's why sometimes they're being called relations in the notes. So this is technically a relation because it's not an actual function. Anyways, we can still find the slope of the tangent line at any point. And I'm going to show you how to do that today. So we're still going to be finding the derivative of this relation here, meaning the slope of the tangent line. But you just have to use the chain rule in a specific way. Okay, so let's do it with this example. I'm just going to zoom in a little bit. So I have more space to write. So this is sort of the typical implicit relation that everyone thinks of when you first learn about this. So this is a classic one, the circle. Okay. So when we take the derivative, or when we want to find the derivative, what we're going to do to both sides of the relation is just apply d by dx. So we're going to take the derivative with respect to x of both sides of this equation. So that's not changing the equation at all because we're doing to both sides. Okay, when we take the derivative with respect to x, the first term is really easy. So we just take the derivative with respect to x of x squared. So we do that like normal. So we'd use the power rule. So the 2 would come down, reduce the power by 1. Now when we take the derivative with respect to x of y squared, we have to use the chain rule. So y is some function of x that we don't know. So we have to think of this as kind of y would be sort of the inner function from our chain rule. And then it's being squared. That's the outer function. Okay, so when we do the chain rule, we would do the outer part first. So the 2 would come down, we leave the y inside, and then we do the derivative of y. We don't know what dy by dx is, but that's fine. So that's sort of the chain rule part of this that you have to wrap your head around. So 2y would be the outer function, and the dy dx is the inner function. If you want, you can also use prime notation, that's fine. And then on the right-hand side of the equation here, we have the derivative of 25. It's a constant. Derivatives of constants by themselves are 0. I'm just going to write here. Or you can write it like this, using this notation, 2y times y prime, whatever you prefer. That's also fine. Okay. Now our goal, remember, is to find the derivative of our function y with respect to x. We want to find this. So now we want to solve for dy by dx. So we're just going to isolate it. So using algebra. Okay, so I'm going to bring the 2x to the other side of the equation. So I'm going to subtract it from both sides. And then 2y is being multiplied to dy dx, so I'm going to divide it on both sides. And there we go. We've got our derivative, dy dx. That is the slope of the tangent line. And if you have a particular point on the curve, you can plug that point in and find the exact slope of the tangent line. We can just simplify it by canceling out those 2's. Okay, good. We're going to do one more example that's a little bit harder this time. Oh, yeah, and let me just show you that it works too. So on our graph in Desmos, so let's just pick a point on this curve, I think 3, 4. And remember our slope was negative x over y. So if I type in point form, negative x over y, so negative 3 over 4, x minus 3, we see we have the tangent line, and here's the slope, negative 3 over 4 for that particular point. Here's my tangent line, so we got the answer right. So you can always check actually by using Desmos. If you've got the right answer, it should look like a proper tangent line. Okay, so here we have an ellipse, x squared plus y squared equals 9 plus xy. We are going to find the equation of the tangent line at 0, 3. So I'm just going to go into my Desmos and set up that equation. You can see it looks like an ellipse. And this time I'm interested in the point 0, 3. I'm going to erase that line. Okay. So there's the point of my line. I want the tangent line. Looks like the slope is going to be positive. Okay, so first, same step as before. Step 1, take the derivative with respect to x of both sides. The right-hand side here is going to be a little more complicated this time. Okay, d by dx of 2x squared is 2x. The derivative with respect to x of y squared is, we have to use the chain rule. So first we're going to do the outer part, the squared part, and then we have to take the derivative of y with respect to x. So remember, y is a function of x. We just don't know what that function looks like. So we just write down dy dx. Okay, now we need to take the derivative of 9, which is 0. And we need to take this derivative of this product. So we have to use the product rule. A lot of students forget to do that. So I'm going to write it in red here. So first we do the x. So derivative of x is 1. And the derivative of y with respect to x is just dy dx. Okay, and now we want to solve for our dy dx term. We have 2 this time, so we're going to bring both of those to one side and all of the other terms to the other side. So I am going to move dy dx terms to the left. So I'll have 2y times dy dx, and I'll have minus x times dy dx. Big line was, okay. And then on the right, I'm going to have y minus 2x. So I'm just going to write underneath what I did here. So I subtracted 2x from this side, and I subtracted x dy dx from this side and this side. Oops. X dy dx. Okay, so I've got all my dy dx terms on one side and all the other terms on the other. Now, how I solve for dy dx here is I factor it out because it's in both terms there, so I can factor it out. And I have 2y minus x and then y minus 2x. And since that's being multiplied, to get rid of that 2y minus x, I just divide. So I have dy dx, so here's my solution, y minus 2x over 2y minus x. I'm just going to check my notes to see if it matches, and I didn't make any mistakes. Yep, good. Okay. So now, so that's the slope of the tangent line at any particular point. We are interested in the point 0, 3. So this is slope of tangent at any point x comma y. So we have a particular point we're interested in, which is 0, 3. So we're going to plug in that point and see what the slope is at our point. Slope at 0, 3. So we'll plug in 3 for y and 0 for x. So 2 times 3 minus 0, which is 3 over 6, which is 1/2. So our slope is 1/2. And we can write an equation. And we'll just use the point slope equation. Oh, actually, we have an intercept here, so we'll use the slope intercept. So it's 1/2 x plus 3, because 3 would be the y-intercept. There we go. So there's your equation. We're going to graph it in decimals just to make sure we've got the right one. Y equals x. 3. There we go. Looks like a tangent. Looks like the correct tangent line to me. So we're all good. Okay, so only 4 questions in your assignment because they do take a while to do, but lots of extra practice if you need it. So there you go.